Hello and welcome. This is Dr. Chris Walinski. I'm the Executive Director of the World Clinical Laser Institute, which is the WCLI. Following this preparatory training course, if you have any questions about this material or are interested in any other future laser training courses, please visit WCLI.org. The purpose of this course is to give you some preparatory material, some background material into some of the more elemental properties and discussions on laser physics and laser safety so that you can maximize the use of your time when you go to your actual live training course. And just like SCUBA is an acronym for self-contained underwater breathing apparatus, laser is also an acronym, and it stands for light amplification by stimulated emission of radiation. And as you might imagine, something like that took someone like Albert Einstein to actually figure out. In 1916, in his quantum theory, Albert Einstein described the theory and the process of stimulated emission of radiation. Well, not to get too technical, but in normal natural occurrences in nature, an atom can exist in an excited state and a resting state. And as you might remember, the excited state is unstable. So what happens in the unstable excited state is that the atom will spontaneously emit radiation in the form of electrons or photons. And this is called spontaneous emission of radiation. Well, if we do this deliberately to a group of atoms, so we take a group of atoms and they're all similar, and so they're either like carbon dioxide atoms or they're erbium YAG atoms or they're erbium chromium YSGG atoms or CO2. What happens is that all of these atoms end up being the same type, and we can deliberately energize them by using something called a flash lamp, or we can use electricity, but we give them energy. And when we do this on purpose, rather than the process being spontaneous, it now becomes stimulated. And instead of just giving up one photon, the excited atom already has one, and you hit it with another one, it gives off two photons. And in a perfect world, this could be a perfect spontaneous chain reaction. But what happens is that a lot of these extra photons that get released end up hitting either nothing or just the walls of the little chamber that these photons are in. But ideally, each one of these would hit another atom and it would cause, an indefinite chain reaction. But this is the basis of how laser radiation or laser light is created compared to normal natural light. And if we just do a very brief history of lasers, we find that back in the mid-60s, when they discovered lasers, the first thing that they'd want to do, what would you want to do? You'd want to cut a tooth, especially if you're a dental scientist. And so what they did was they discovered the CO2 laser, and they started to cut cavity preps in beagle dogs using the CO2. And what they found was that the CO2 cut teeth really well. But in every single case, the teeth had to be extracted because the CO2 laser energy also was absorbed not only in the hydroxyapatite of the tooth, but also in the pigment of the dental pulp. And so what had happened at that point was they decided, lasers are neat, but they can only be used in dentistry in soft tissue because otherwise they're going to melt enamel and burn bone and cause all sorts of thermal damage to our natural biologic tissue. And it wasn't until 1989, with the introduction of the erbium family of lasers, that they actually started to use lasers in dentistry. The difference is the CO2 is absorbed into water, hydroxyapatite, and pigment. Well, when we get to 1989 and the erbium lasers are introduced, the erbium YAG and the erbium chromium YSGG, all these things will start making sense as we move along. But as the two erbium wavelengths were introduced, those are only absorbed by water and hydroxyapatite, not pigment. So now we can cut teeth because of the absorption mostly in the water and hydroxyapatite without actually damaging the pulp of the tooth because we're not getting any absorption into the pigment. So just as an atom is the smallest particle of matter, A photon is the smallest particle of light, and that's actually what creates any light, whether it be normal natural light or laser light. And by definition, a photon is the elementary particle or quantum of radiant energy and makes up all forms of light. So other definitions that are important as we get into lasers is wavelength. And as we look at wavelength, the wavelength is measured from either, say, crest to crest or peak to peak or valley to valley, but it's essentially from one corresponding part of the wave to the next reoccurring part of that same wave. And when we're discussing dental lasers, these wavelengths are very, very short. They're actually on the order of 10 to the minus 9, which is called a nanometer. So a nanometer equals 10 to the minus 9 meters. It's very, very short. But this also allows that the laser energy will be able to hit tissue, target tissue, whether it be soft tissue or hard tissue, and actually cause ablation. And the definition of ablation is the surgical removal of tissue, in this case by a laser. So as we look at a particular portion of the electromagnetic spectrum, we see on the left side is ultraviolet or UV, and then there's the visible spectrum, and on the right is the infrared or IR. And as we start to look at what types of lasers are in these areas, there are actually laser wavelengths in the UV spectrum. Excimer laser comes to mind. It's something used in ophthalmology, and excimer lasers actually will cut teeth. But why don't we use them in dentistry? Because it's ionizing ultraviolet radiation. So as we move into the visible spectrum, we see that there are a couple wavelengths in the blue and in the green where argon lasers exist. And traditionally, like back in the olden days, actually it's probably been about 15, 20 years ago, there was an argon laser that was used to polymerize composite materials, but because these wavelengths are so specific, it didn't always match up with the photo initiator within the composite, and then if it wasn't exactly right on, then the composite didn't cure. But when it did work, it worked wonderfully, because in 2 to 3 seconds you got a very deep, very permanent cure of the composite resin. The green argon wavelengths are used in surgery. They're soft tissue lasers. And then as we move on into the red, most of the lasers, actually all of the lasers that we use in dentistry, are invisible to the human eye. So all of them come with something called an aiming beam. And sometimes the aiming beam is green and sometimes the aiming beam is red. But this shows us that, number one, the fiber is intact. It shows us that our tips are intact. It shows us that everything is working the way it's supposed to. And in some cases, it will actually even show us exactly where we're cutting or where we're about to ablate if we have to hold our tip a little bit further away from the tissue. The other notable thing about the red and the green is that there's something called low-level light therapy or photobiomodulation or biostimulation. Everyone's pretty much agreed, though, on the term photobiomodulation therapy. And this is using very deep penetrating wavelengths of light, including the red and the green, to speed wound healing and to increase the release of endorphins and ATP production, and basically to improve wound healing and speed the healing. And that's why one of the reasons why using lasers is so beneficial. And this is not just some mad scientist. There are over 4,000 papers published, and over 350 of them are randomized, controlled, double-blinded studies. They come out on the order of about 30 to 40 papers a month at this point, just because it's become such an interesting part of laser science. Then as we move into the near infrared, we call it near infrared because it's very close to the visible spectrum, we see that's where diode lasers are. And diodes are about between 800 and 1,000 nanometers. No matter which diode you may have or you may be looking at, they're all between about 800 and 1,000 nanometers. Diode lasers are absorbed into soft tissue, and the reason is that they're actually used in soft tissue because they're absorbed into pigment primarily, but also to a lesser extent water, and that's important to us as we move forward. As we get to the mid-infrared, I forgot about Nd:YAG. Nd:YAG is at 1064. It's very close to diode, but it operates very differently. As we get into modes of operation, I'll explain the difference between how a diode and an Nd:YAG work. And then when we get to the mid-infrared, around 3000, we see the erbium-YAG and the erbium-chromium YSGG, which is the water lasers. And these now, instead of being absorbed into pigment and water, like the diode and the Nd:YAG, these wavelengths are absorbed primarily into water and hydroxyapatite. So the hydroxyapatite, obviously, it will absorb into teeth to cut teeth, and the water will get absorbed into the soft tissue, because soft tissue is primarily made out of water. And then as we get to out into around the 10,000 range, anywhere from 9,300 to 10,600 nanometers, we end up seeing the CO2 wavelengths, and that's where we get absorption into all three of the chromophores: the water, the hydroxyapatite, and the pigment. So how is laser light different than ordinary light? Well, ordinary light is all different wavelengths. That's why it's usually white. It goes in all different directions. It's non-focused. And so there's really a big difference between normal, everyday light and laser light. So speaking specifically about lasers, there are three properties that I want you to be aware of. Number one, laser energy is said to be coherent. What does this mean? This means that, remember the Einstein theory on stimulated emission of radiation? Well, what happens is that all of those photons come out of the exact same atoms or compounds, whether it be CO2 or a crystal like erbium-YAG or Nd:YAG. All of the photons have the exact same properties, which means that all of the photons vibrate in the same energy pattern, and they all move in the same kind of in phase, and therefore they're synchronized when they move, and therefore it's called coherent light or laser light. Secondly, laser light is said to be monochromatic. Because all of those photons come out of the same material, all of those photons have the same color, so laser light has only one color. And finally, it's also collimated, meaning that all of the photons move in a straight line. That being said, laser light by definition is collimated. So if you're asked, is laser light collimated or is it divergent? It is collimated. However, once that collimated laser light goes through the fiber and gets bent in different directions and comes out of your handpiece and hits the tooth, it's no longer collimated. At that point, once it's gone through the fiber and it's been bent and it comes out the handpiece, now it becomes divergent. And what that means is that the further away from the tip you are, the less energy you're able to affect the tissue with. So that's one of the ways that we're able to cut faster and slower. If we move the handpiece close to the tissue, we'll cut faster. And if we move the handpiece away from the tissue, we'll cut slower. And moving the handpiece farther away from the tissue is called defocusing the handpiece. A couple of other definitions as we move through different laser basics. One is called active medium. And as I've been talking about Nd:YAG and erbium-chromium YSGG, that is active medium. So there's two different ways to name a laser. One is by the active medium, and the other is by the wavelength. And both of them mean the same thing. It's just two different ways that we describe a laser to our colleagues when we're discussing different dental treatments that we're doing. There are also different types of lasers. There's solid-state lasers, gas lasers, liquid dye lasers, and diode lasers. There are no liquid dye lasers in dentistry. There are gas lasers. As we mentioned, there was an argon, and there's CO2 lasers. Diode lasers are a different animal in that they don't use an actual crystal like the erbium-YAG and the Nd:YAG and the YSGG crystal. What they use instead is a semiconductor chip that is powered by a positive and negative electrode, and then you can dial in the specific wavelength that it is that you're trying to, well, you can't, but the manufacturer dials in a specific wavelength, and that's how you determine which wavelength you're using. And so what happens is that because it's an electronic device as opposed to a device that uses a different form of energy, called a flash lamp, then you can end up having diode lasers that are very small. And in fact, there are some diode lasers in dentistry that are no larger than a Sharpie marker, and they're very convenient and very portable. So we get into some just basic rules of laser light. Number one, I mentioned already that lasers by definition are collimated, but once laser energy exits the fiber, it's no longer collimated in dentistry. And then divergence, that means that the farther away you are from that tip, the less energy there is, and the closer you are, the more energy it is. So think about divergence like if you have a flashlight and you have it very close to a surface, it's a small bright spot. And then as you move the flashlight away from that wall, the spot gets bigger and bigger, doesn't it? But it gets more dim. So there's fewer photons in the big spot as in the small spot, and that affects our spot size and our power density. And then as we move along, laser light will travel in a straight line, and this is traditional laser light. This is not necessarily from a dental handpiece. So think about laser pointer for a moment. That laser light will travel in a straight line until it's either absorbed by something, it's reflected by something, or it's refracted by something. And then finally, just a basic tenet of lasers is that you should always use the lowest power setting that will achieve your desired result in a reasonable amount of time. And the reason for this is that if you use unnecessarily high power outputs in your laser, you're more likely to cause thermal damage to the tissue. So a few more definitions. Number one is hertz. And this is the equivalent of how many pulses the laser puts out per second. So how many times does the laser go pop, 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 pop per second? That's the hertz rate. So these are interchangeable, either PPS, pulses per second, or hertz. Secondly is joule. Joule is a unit of energy, and it's the ability to do work, whereas watts are a unit of power, and it's the rate of doing work. So because it's a rate, these two are related by time. In other words, for every watt that your laser is putting out, that equals 1 joule for 1 second. So let me just kind of rephrase that. If your laser is firing at 2 watts, then it's putting out 2 joules every second. If it's firing at 3 watts, it's putting out 3 joules every second. So every second it's putting out 3 joules and 3 joules and 3 joules, which equals 3 watts. And then if you divide it by the number of pulses per second, because you can change the number of pulses per second from like 5 to 100. So let's say it's pulsing 10 times every second. So it's at 10 hertz. So it's going pop, 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 10 times every second. If, say, you're at 2 watts, okay, so you're putting out 2 joules per second, if you kind of extrapolate that, 2 joules equals 2,000 millijoules. And then if you divide 2,000 millijoules by 10 hertz, by 10 pulses per second, you come out to 200. What does that mean? Each one of those pulses equals 200 millijoules per pulse. So that means after 1 second, you've had 10 pulses, each of them worth 200 millijoules per pulse. That totals 2,000 millijoules, which therefore equals 2 joules per second. And that's how you kind of go back and forth between millijoules and watts. And peak power and average power are two different things, and I'll get into that as we start talking about the different modes of operation as well. But the peak power and the average power is another way that we can distinguish between, say, a diode laser and an Nd:YAG or a water laser, for instance. So in our example before, I was using 2 watts, but if we use 1 watt, which is 1 joule per second, okay, and we only have, let's say we could put our laser to 1 pulse. Well, One pulse would be 1,000 millijoules per second. Actually, they're all 1,000 millijoules per second. But how do you divide that up? Well, if you only have one pulse per second, then that one pulse would be 1,000 millijoules. If you had 2 pulses per second, then each one of those pulses would have to only be 500, because you've got 500 for one and 500 for the second, and that equals 1,000. So 4 pulses, each one is 250. 10 pulses, each one's 100. 20 pulses, each one's 50. I think you see how this relates now. So if we're at 10 pulses per second and it's 1,000 millijoules in that second, therefore each pulse is 100 millijoules. And the reason I'm telling you this is not so much so that you can operate your device, it's so that you have an idea of, you're reading a paper. Most papers will tell you not so much that it was using 2 watts or 3 watts or 4 watts, it's telling you how many pulses, how many millijoules per pulse, and that makes more of a difference. How else would I, if you put a cake in the oven at 400 degrees, well, you'd probably burn it. So if you put a cake in the oven for, let's say, 350 degrees for an hour, let's say 60 minutes, you could also put that cake in the oven at 3,500 degrees for 6 minutes, and you'd end up getting the same total energy, but it has a very different result. So what I'm trying to maybe explain here is that as you're reading the papers and you see that a particular study, they did something at 250 millijoules per pulse, now you'll know how to do the math in that case. And different products have different ways to explain this. In this particular product, which is not yours, you see that the 2 variables that you can change are either the hertz or the millijoules per pulse. So power density is different than power. Power is the power. That's kind of stupid, I'm sorry. But the power that you put on the machine is 3 watts, it's 4 watts, it's 5 watts. That's the power. But the power density can be different from tip to tip. And it's because if you have a really fat tip or you have a really skinny tip, even though the same amount of energy is coming out, you're going to have different power densities. The thinner the tip, the higher the power density. Think about if you have, say, 5 gallons a minute coming out of a big hose, it's probably just going to trickle out and hit the floor. But if you have that same amount of water coming out of a really tiny hose, it could go 20 feet to the back of the room and hit the wall. And the same thing happens when laser light gets concentrated in a small tip. The smaller the tip, the higher the power density, and it's different than the power. And it's measured in watts per centimeter squared. Another example of how the spot size or the size of the tip can change the amount of energy or the amount of power that you're using is in this example. In both of these examples, we have 5 watts going through, so that the laser power is 5 watts. But the power density is different. You see a 400 micron tip, and there is a tip called an MT4, which is 400 microns in diameter. So 5 watts right at that tip would be about 6,000 watts per centimeter squared. Now, if you defocus that tip, if you move that tip away from the tissue about a millimeter, that 400 microns, think about the flashlight example, it would start to get bigger and bigger. And it would get to be about a millimeter spot size. So instead of 0.4, it would be 1.0 spot size. And in just moving it back by about 1 millimeter, your power density drops from 6,000 watts per centimeter squared to 600 watts per centimeter squared. If you move it another millimeter away, it's going to go down to 6 watts per centimeter squared. You still got 5 watts coming out of the laser, but because you've moved your tip far enough away from the tissue, it's not going to do too much when you're trying to cut something. And the 2 things that almost every single new laser user does incorrectly, I find, number 1 is that they keep their hand too far away. They're afraid of damaging the laser or damaging the tooth or damaging the tissue. I'm not sure what it is, but I see them holding the handpiece 2-3 millimeters away from the tissue. And secondly, you spent your whole career using a high-speed handpiece. And when you do, there's a certain speed of movement of a high speed with a rotating burr. Well, I'll tell you that you have to move the laser handpiece quite a bit slower in order to achieve any sort of appreciable ablation of the tissue. So in other words, just slow down. I would rather during your initial training you moving too slow. But I guarantee you that once you start using the handpiece, because it looks like a dental drill and it feels like a dental drill, you're going to start moving at the same speed and it's not going to cut as well. Just slow down. The slower you move, the faster that it will cut. And then as we talked about absorption into water and pigment and hydroxyapatite, if we look at an actual kind of chart of active media on the left-hand side, left-hand column, and then the wavelengths associated with that in the middle column, then we can see what types of material that these wavelengths are absorbed into on the right-hand column. So if you look down, you see erbium lasers at 2780 nanometers. That's your water laser, is absorbed primarily by water and hydroxyapatite, which is why it cuts soft tissue and hard tissue. So it's not by any, it's not a coincidence. These lasers were made specifically for absorption in these particular biologic materials in order to get the best biologic effect. So there's a couple of different delivery systems that I'll bring your attention to. One's called an articulated arm, another is a hollow waveguide, and the third is an optical fiber. So starting off with the articulated arm, this is very similar to an X-ray arm, the arm that holds your X-ray, where there's little bends in it. Not little bends, but there are bends in the arm. And inside this, there are mirrors, so the laser energy comes out of the unit and it bounces off these mirrors, and then it uses a focusing lens at the end to actually concentrate the beam. The issue with this is that, as you can imagine, it tends to be kind of a bulky setup and makes sometimes for intraoral use a little bit impractical, just because there's usually something that's pretty large on the handpiece, and sometimes getting to certain areas of the mouth can be a challenge. But that's called an articulated arm. Second is a hollow waveguide, and this is basically a hollow tube that's lined with a metallic reflective substance, and the laser energy basically bounces off the inside, because even though it's laser, it does start getting bent, and then as it does, it comes out the end of the waveguide, and that's how some of the lasers are delivered. And the way that your laser is delivered is through an optic fiber. And so the optic fiber has the actual core, which is a piece of glass. So the black fiber, the thick fiber that's on your laser, actually has a very thin piece of glass embedded on the inside of it. And then it's covered by a couple of protective layers so that that fiber can bend. But obviously you can't bend it really into an acute angle, because otherwise you will snap that glass fiber inside, which is why you should never take it off of that the support bar that it's sitting on. And so what happens is that the laser energy goes through this fiber and comes out the end of the core, and it's a very efficient way to deliver laser energy. And that brings us to the end of our first module. So at this point, you can either take a break or you can proceed directly to the second module, starting with the laser modes of operation.